Okay, good morning, gang. Why did that? Oh, yeah, that didn't. Okay, so I just noticed that the Zoom meeting says it starts at 10. That's not correct. I don't know why it moved to that, but it looks like pretty much everybody is here. We've been doing this long enough that I'm sure you guys are comfy by now. So let's flip it over to, oh, my DocCam software isn't running yet. Before we get into things today, I owe you guys an apology. I am working on your exams, but they've been a little bit tougher to grade in this format than I expected, so I haven't quite finished, and I will ask for your patience. I will get them done today, I can assure you of that, but I don't have them ready quite yet, so I'll ask you to wait a little bit longer, but I promise you'll see those grades and all my comments scanned and everything uploaded today. Okay. So I don't have them to hand back to you right now. I suppose it's not super important because we don't have a physical class, but before the end of the day today, you'll see everything uploaded. And right now, we're going to continue talking about differentiation. I guess a few other comments on exam. On exam one. So I'll have the scores and feedback in Canvas by the end of day today. A few people asked about, and I think I mentioned in class once, the possibility of some way of earning some points back on this test if things didn't go especially well for you. And the feel I have from what I've graded so far is that that may end up being something I feel compelled to do. It looks like a number of folks didn't quite have time to answer all the free response questions. And I really do want to see what you guys know. I want to see your work on those things. And if the trend that I'm seeing so far continues, where a meaningful percentage of people did not have time to even attempt all the problems, then I will think of some way, some sort of project or something that you guys could do that I might be able to see your skills on those questions that you weren't able to get to. And that will kind of soften the grades a little bit. So I try not to panic while we wait here. It's likely that I will have some sort of like rewrite to allow folks to improve their score. I've never done this before, but these are weird times, and you know, I want to be sensitive to that. My goal here is not to stress anybody out. I certainly don't want you so stressed that you feel tempted to cheat or anything like that. My goal is to teach you calculus and to see that you've learned calculus. So this is what I want to see. It's going to take me a little while to figure out how the hell to do this. Like I said, because I've never felt compelled to do it before. But from what I've seen so far, there are enough people who weren't able to give a full effort on all of the free response problems. And that's not satisfying to me. I imagine it's really not satisfying to you. And I want to make sure that we all have a good experience here, at least as good an experience as we can have. So that's where we're at with that shit right now. So the raw grades will be in today. And then I will continue to think about what exactly we could do. What I'm leaning towards is putting together a few similar questions so that you guys could work through them and send me that work, and then I could average the grades or something like that between the reworked questions and the questions that you did during the test. On the other hand, you know, I don't want to be unfair to the people who worked really hard and studied and were able to get everything done. So it's going to take a little bit for me to figure out exactly how to do that, but I don't want you guys to panic. And I want you to know what I'm thinking. So that's what I'm thinking right now. Other little comments here. There are some places where I can tell that the work that was submitted isn't 100% our own. I'm not saying everybody did this, and if you know, don't feel attacked. I'm not coming after anybody. I haven't seen anything here that's so offensive to my ethics that I feel compelled to start a case about it or anything. But please don't cheat. I assure you, I will always be as forgiving as is humanly possible when it comes to grading these things. And it really matters to me that I see your work, because if I don't see your work, I can't give you good feedback. And if I can't give you good feedback, then you can't improve. And so if you Desmos or Symbolab your way through this class, then it will catch you out in Calc 2 really, really bad. And if I let you do that, I'm doing you a disservice. So I know that it's very hard to police this sort of thing, especially in the online setting. And so what I would like to do is offer you my hand and guarantee you that I promise I will be gentle enough that you don't need to cheat. And if you show me your actual work, I will be able to help you more. So if you ever feel compelled to do something like that, remember this moment, right? Remember what I'm saying here is that, that if you put forth a sufficient effort, you can learn this shit. The best way for me to help you learn this shit is to show me what your actual skills are, and then we can work together to fill in the gaps. So just a few little things there. There's nothing that's huge, but every now and then I see like a step. Oh, that step's clearly from Symbolab. That's a bummer. You know, that sort of thing bums me out. Nothing here bad enough for me to start what do you call it? Ethics case or a conduct trial. But I see it, you know, and I know when that's what's going on, and it makes me a little bit sad. So don't feel bad. A lot of people find themselves in that position where they feel like they're up against a wall and they have to do something, rather than saying, if you make this mistake up against the wall, I'd like to just move the wall a little bit. So trust me that I'm here to help you, and don't feel compelled to do anything like that in the future. If you happen to have felt compelled here, try to relax and remember I'm on your team, and the best way for me to help you is for you to be honest with me about your skills. So the place we left off last time was implicit differentiation. Implicit differentiation runs into logarithmic differentiation, and then we'll start talking about applications. So the section we're going to begin today is section 3.5. On logarithmic differentiation. And back when I took this class, logarithmic differentiation was just a subsection of the implicit differentiation section. So at the end of class on Friday, we saw how to take the derivative of f of x equals ln x. And the game here, actually, let me call this y equals ln x. That way the notation will look a little bit cleaner. The way we did this was by making use of some properties of the logarithm and then differentiating implicitly. And that gave us an equation that we could then solve for the relevant derivative. It was very similar to how we found the derivatives of the inverse trig functions. Remember, y equals ln x is equivalent to e to the y equals x. This is the definition of the natural log. And then we can differentiate implicitly. So because e to the y equals x, therefore, d dx, e to the y, the derivative on the left, equals d dx of x, the derivative on the right. So I take y equals ln x, and I rewrite it in this way. And then I differentiate implicitly with respect to x on both sides. the derivative of e to some stuff is always that stuff times, or sorry, e to that stuff times that stuff primed. And the derivative of x taken with respect to x is just 1, which means y primed is 1 over e to the y. But e to the y is x. So this is the same as saying y primed equals 1 over x, i.e., that is, if you want to differentiate the natural log of x, that derivative is 1 over x. And this relationship is actually how we define the natural log in a slightly more grown-up math class. In an analysis class, we define the natural log as being the guy whose antiderivative is, the guy whose derivative, sorry, is 1 over x. It's usually discussed in terms of areas, but that's the first big point in section 3.5. So that the derivative of the natural log is 1 over x, which is kind of surprising. Most of the transcendental functions we've seen don't have algebraic derivatives, right? That on its own is kind of neat, right? Like the derivative of sine, cosine, secant, tangent, all of those transcendental functions have transcendental derivatives. Like the derivative of your trig functions is some other combination of trig functions. Derivative of e to the x is e to the x. But here you have a transcendental function, the natural log of x. And when you take the derivative, you get something that's like remarkably simple. You know, it's just straight algebra function rather than some weird trig log exponential thing. And that's a useful property in a lot of ways. But what section 3.5 really gets into is how to use properties of logarithms together with the chain rule to differentiate really nasty functions. So that's where we're going to go with this. While I'm opening the textbook here and finding some more examples for us to play with, I'll remind you, if you need more time on the homework from last week, that's totally understandable. Just submit an extension request in WebAssign, and I will go through today and clear all those out. The other thing that we're going to talk about this week is related rates, which is a bit of a challenging subject for a lot of people because it requires a bit of like physical intuition. Sorry, I got the section number wrong. This is section 3.6 on logarithmic differentiation. Yeah, 3.5 is the implicit differentiation section. So what do I mean when I say like we can differentiate nasty stuff using properties of logarithms? I'll first remind you those properties of logarithms that we're going to make use of. So there's the definition of the logarithm, which says that the b raised to the base b log of some stuff is always just that stuff, and the base b log of b to some stuff is always just that stuff. Right, these are the definitions of, this is the definition of the base b logarithm. And you can think of that as a property. But then the ones that we're going to make a lot of use of are things like this. So if I have the base b log of, how should I write this? X, and let's call it, yeah, x to the y. That's the same as y times the base b log of x. So powers inside of a logarithm are the same as multiples outside. As long as everything in that logarithm is raised to that power, you can pull that power down front. And then we also have a rule that says logs, regardless of the base, with a product inside. This is the sum of the logs. So multiplication inside is the same as addition outside. And there is one more rule here that you could get by combining these. If you have a log of a ratio, that's the difference of the logs. So division inside is the same as subtraction outside. Right, so these are the properties of logs that we're going to be making use of. And the idea here is I give you something ugly to differentiate. You take the log on both sides, expand everything out into a bunch of simple log functions, and then differentiate each of those. I'm gonna turn on some light here and grab my coffee, and we'll do a nice example. Okay. So there's a bunch of fun things we can use here. One of my favorite examples is x to the x, but maybe we'll start with something a little more tame. 6, nah, oh, that's brutal actually. I suppose we should do that too, yeah. Yeah, let's start by finding the derivative of an arbitrary base logarithm. And then we'll take a look at what the chain rule says. So can we find well, order here. Yeah, let's start with this, yeah. I want to find this derivative. So you've seen that the derivative of the natural log is 1 over x. There's more than one way to get at the arbitrary base logarithm's derivative. If y is the base b log of x, I'm just going to do the same thing that we did for the natural log. Then b to the y equals x. And I can differentiate implicitly on both sides. The derivative of x is 1. The derivative of b to the y, remember how to differentiate the arbitrary base exponential. That's b to the y times the natural log of b. This is something we did 2 meetings ago. And then you'll have, oops, sorry, I'm running out of space here. I'll write this over here because I ran out of space. So the derivative on the left is b to the y ln b. That's the derivative of the outer function. And then I have to multiply by the derivative of the inner function, which is just y prime. So we're differentiating implicitly with respect to x. The derivative of b to the x would be b to the x ln b. So the derivative of b to the y is b to the y ln b times y prime. And on the right-hand side, we get 1. So then you solve for y prime. And that means, remember, b to the y is x. So this is 1 over x ln b downstairs like that. In other words, the derivative d dx of the base b logarithm, you get your 1 over x, just like you would with the natural log, but then you have this additional factor downstairs of the natural log of b. Right, so your book uses this as the first example. It's not a kind of typical logarithmic differentiation problem, but it is good to know, right? It's good to know how to find the derivative of any log function you wanted. I would argue that there's an easier way to do this using the change of base formula. I'll show you what I mean, and then we'll look at a more challenging problem like this. So if you don't like the approach, you could also use the change of base formula. That says that the base b log of x could be written as any base logarithm you want. You could write it as an ln, for example. That's ln x over ln b. Therefore, and here you can just apply the differential operator d dx to both sides right away. This is how I prefer to come up with this thing. Remember that ln b is just a number. It is a constant. It is not a function. Or it doesn't change with x, so I can pop him out of the derivative. And then the derivative of ln x I knew from previous work is 1 over x. This is 1 over ln b times 1 over x, which is the same thing we got before. It's the same as 1 over x ln b. So your book shows you how to get the derivative of the arbitrary base logarithm function this way, which has some merits. It's notably the same trick that we use to get the derivative of the natural log. And so in that sense, it might be a bit more familiar. But I prefer this attack. Either way, what I would ask for you to remember from this example is just the result, that the derivative of the arbitrary base logarithm function is 1 over x times the natural log of the base. So the derivative of log 2 or log 3 for example, here the derivative of the base 2 logarithm would be 1 over x times the natural log of 2. Nothing too crazy here. We can apply the chain rule to log functions the same as we can to anything else. And this is moving in the direction of the sort of things we usually do with logarithmic differentiation. For example, if I wanted to find d dx of the ln of the sine of x, this will require a chain rule. My outer function is the ln. My inner function is the sine function. So if I differentiate the outer function, leaving the inner function alone, the derivative of ln is 1 over x. So the derivative of ln sine x is 1 over sine x. And then by the chain rule, I need to multiply by the derivative of the inner function. So I differentiate the outer, leaving the inner alone. Derivative of ln stuff should be 1 over that stuff times that stuff primed. That's the chain rule. So I'll write it out like this. But then the derivative of sine is cosine. So this is 1 over sine x times cosine x. Or another way to say that if you want to is cosine x over sine x, that's cotangent x. And there are some surprising connections between logarithms and trig functions. You'll be able to read more deeply into those when you get into Calc 2. But this is kind of the first hint that something like that might exist. there is a more general result here that's worth sharing. Just like we talked about general chain rule derivatives of exponentials, I would like to talk about the general chain rule derivatives of logs. But first, questions on either of these examples on the screen right now. Is there anything here that feels wonky or you guys would like to talk about?
Do you think you could go over the first step again on that example?
Here?
Yeah, right there.
So I'm using the chain rule. If I want to differentiate the ln of some stuff, remember the derivative of ln x is 1 over x. So the derivative of the ln of sine of x should be 1 over the sine of x times the derivative of sine by the chain rule.
Okay, I got it. Thank you.
Make sense? And then, yeah. So I'm glad you asked that, because the very next thing I wanted to do here was talk a little bit more generally about that. If u is a function of x, then d dx ln u should be, well, if I differentiate the outer function, the ln, I get 1 over whatever's inside. So I'll have 1 over u. But then by the chain rule, I have to multiply by the derivative of the inside. So just like we had that general derivative, e to the u, if you want to prime e to the u, you always get e to the u times u prime. Well, the derivative of ln u is always 1 over u times u prime. Or some people remember this as u prime over u. So the derivative of a log is always 1 over the inside times the derivative of the inside. And that's the chain rule. This is something that you might want to hold on to.
This might seem like a silly question. What's the difference between the derivative and prime?
What's the difference between the derivative and what?
Prime.
Oh, there is no difference. Yeah, prime is just a notation for the derivative. Yep.
Just checking. Okay, thank you.
Yeah, no problem. It's weird. The derivative is weird because we've got like 4 different notations for it, right? We've got the prime notation, and then we've got the ddx notation. It can be a little bit overwhelming at first. And believe it or not, physicists have more notation still that they like to use for derivatives. They use dots. So yeah, no, totally understandable. I want to look at a slightly more complicated example this time. So let's do it. So here's the first time I'm going to use those properties to help me with a derivative, those log properties. So I want to find the derivative of the natural log of x plus 1 over x plus 2. And I could jump right in with this rule at the top here. If I was feeling brave, there's nothing to stop me from doing that. But if I use my logarithm properties to simplify this algebraically first, I can get a much easier thing to differentiate. That logarithm, I'm going to forget about the derivative for a minute and just do some algebra. The log of a ratio, if we look here at that fourth rule, log of y over x is log y minus log x. So I can split this log up. I can expand as ln of the top minus the ln of the bottom. And that way, when I go to differentiate, I can differentiate either of these two pieces on their own and then subtract them rather than doing some huge quotient rule inside my chain rule. And it gets better. I can do something with this square root also. remember that the square root is the same as the 1/2 power. So the inside of this logarithm is x plus 2 raised to the 1/2 power. And I can bring that power down. So this function is identical to the function that we want to differentiate. But holy shit, look how much easier it's going to be to differentiate this than it would be to differentiate this. This is the miracle of logarithmic differentiation. Logarithms, so what sort of things are hard to differentiate? Big products and big quotients, things that require use of those messy differentiation rules. Well, if you take the log and expand everything, then you get rid of all the products and you get rid of all the quotients. That's what logarithms do. Fundamentally, if you want like a good intuition about logarithms, they get rid of multiplication and division. They turn multiplication into addition. They turn division into subtraction. So fundamentally what the logarithm does is it makes it nicer to differentiate. It gets rid of the things that are hard to differentiate. If I wanted to dive right in and calculate this derivative, your textbook does it, I'll show you. You need a bunch of product rule and quotient rule stuff. Ah, shit, where is it? Where are we? We are here, right? So if we wanted to dive right in, we would need to use the rule for the logarithm saying, okay, you take 1 over the inside, that's this piece, and then you multiply by the derivative of the inside. All right, well, 1 over the inside, that's looking kind of complicated on its own. And then this derivative right here is going to be a nasty quotient rule derivative. Holy fuck, no thanks. So rather than do that, we expand this logarithm and then differentiate. So because the logarithm of x plus 1 over square root x plus 2 is equal to this, the derivative of that logarithm is equal to the derivative of this. Like so. And now the pieces over here are easy to differentiate. Of course, I take the derivative of each one on its own, so I'll have d dx ln x plus 1 minus 1/2, the constant comes out, d dx ln x plus 2. And according to my rule at the top here, d dx of ln x plus 1 is going to be 1 over x plus 1 times the derivative of x plus 1. And the derivative of x plus 1 is just 1. The derivative of ln x plus 2 is going to be 1 over x plus 2 times the derivative of x plus 2, which is also 1. Let's see how much simpler this is. So I get 1 over x plus 1 minus 1 over 2 times x plus 2. That 2 in the second fraction here is coming from the 1/2 above. Way nicer. You could have a common denominator here if you wanted to, and if you were trying to do something like find horizontal tangent lines, you should. So just for algebra practice, let's go ahead and glue those pieces together. This piece is missing the 2 and the x plus 2. So I'll recap down here, d dx ln x plus 1 over the square root of x plus 2 is equal to 1 over x plus 1 minus 1 over 2x plus 2. And this piece I'm going to multiply by 2x plus 2 over 2x plus 2 to have my common denominator. And this piece I'll multiply by x plus 1 over x plus 1. And so finally, if I'm trying to simplify my derivative as much as possible, I'll have 2 times x plus 2 minus 1 times x plus 1 all over x plus 1 times 2x plus 2. And then I'll distribute this 2 upstairs. So I'll have 2x plus 4 minus x minus 1. So I distribute this negative also. Downstairs, maybe I'll write that denominator as 2 times x plus 1 times x plus 2, just writing the constant term out front. 2x minus x is 1x. And 4 minus 1 is 3. So this is where we end up. And for my money, that is a lot nicer than the thing that you would get if you tried to jump in right away using the chain rule, the quotient rule, and then within the quotient rule, more chain rule, as would be called for if you tried to take the derivative kind of barehanded without doing any algebra first. I'll show you what I mean here. I don't think it's very easy to see. They've got a minus 2 here rather than a plus 2, so their numbers are a little bit different. But I don't think it's easy to see that this object, which is what you get by jumping in barehanded, will simplify to this. The simplification step from here to here is hard. Forget about how hard the derivative step is, that's challenging on its own. But just simplifying your derivative into this piece is challenging. Whereas if you do this first, life is easy, life is good. So questions on this derivative, or on how we simplified the derivative, on the algebra that we did in order to make the derivative easier to calculate? Anything like that?
In the second to last step, how did we get the multiplied by 1 there?
That's the chain rule. So this 1
Oh,
is
the
coming from
derivative.
the derivative of the inside. This is x plus 1 primed. And this is x plus 2 primed.
Nice, I see it now, thanks.
Yeah, of course, no problem. Any other questions on this fella? So what I hope you're seeing is that if you expand a logarithm, it's much, much easier it's much easier to differentiate the thing after you expand. And that's the heart of section 3.6. So here I'll show you what a kind of standard logarithmic differentiation problem looks like. It doesn't begin with any logs. When I hand you the problem, I'm just going to say, differentiate y equals, and then there's some huge scary looking mess, like the textbook has the example here, x to the 3/4 times the square root of x squared plus 1 all over 3x plus 2 to the 5. Now, the good news is that if you didn't have logarithmic differentiation, but you are well practiced with the product and quotient rules, then you could still come in here and do this. You're going to have a bad time, but you could do it. Now we have a little bit of a different perspective, though. If I take the natural logarithm on both sides and then differentiate implicitly after expanding the logarithm, I'll have something that's much easier to work with from the calculus perspective. If I wanted to calculate y prime directly using the quotient rule here, it would take about 15 minutes because the whole thing is a big quotient. And then within that, right, the top has a product, the bottom would require chain rule stuff. So everywhere you have like low d high, well, the d high, the derivative of the top here can go fuck itself. It's horrible, right? It's a product rule. And inside that product, there's a chain rule. Like, no way. So instead of that, I say, all right, I'm gonna take the natural log on both sides. And then I'm gonna expand this as much as possible. So you remember in your algebra classes when there were those horrible problems like expand this log all the way out here, and you're like, why? Why would I do this? This is why. That's the same as the ln of the top minus the ln of the bottom and you notice my ample use of parentheses. I recommend you do the same. Always show what the inside of the log is using parens. And now each of these pieces I can do some more shit with. Here I've got multiplication inside that can be turned into addition outside. I've got a power here that can come down. So I'll write this as ln of x to the 3/4 plus ln of square root x squared plus 1, which I'll write as x squared plus 1 to the 1/2 minus ln of 3x plus 2 to the 5. And then one last step, simplifying things with log properties. I'll bring all those powers down in front. So hopefully this is stuff that you mastered in your algebra classes. If not, it is time to master it. We're still gonna need a little bit of chain rule for the middle guy. Actually for both of these guys on the right. But it's much, much simpler than it would be if we tried to jump in right away. So first, I take ln of both sides. Then expand. And then finally, I differentiate. So what is it I'm going to differentiate? Well, I have ln y equals all this stuff. So d dx of ln y equals d dx of all this stuff. Like so. Everybody with me? On the left-hand side, I'm differentiating implicitly. So this will be 1 over y times, by the chain rule, y prime. On the right-hand side, I'll have 3/4 times the derivative of ln x is 1 over x plus 1/2 times the derivative of ln x squared plus 1. Well, that's going to be 1 over x squared plus 1 times the derivative of x squared plus 1, that's 2x. And then minus 5 times the derivative of ln 3x plus 2. That's 1 over 3x plus 2 times the derivative of 3x plus 2, which is 3. And then I simplify as much as I can. This gives me 3 over 4x plus. Here, this 2 from the 1/2 and the 2 from the 2x cancel, and I just get x over x squared plus 1 minus, here I've got 5 times 3 is 15 over 3x plus 2. Now we're almost done. I have to multiply both sides by y, right? Because right now I've got 1 over y times y prime equals this. So that means y prime is equal to y times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And that's an acceptable answer if you're okay with having your derivative defined in terms of both x and y. But really what I want is a nice formula for y prime that only has x's in it. So I come all the way back up here, y equals that thing. Zoom out a little bit so you can get it all on one page. So right now I have y prime equals y times this stuff. I'm going to replace this y by what it is. And that will give me the final result. Y prime equals x to the 3/4 square root x squared plus 1 over 3x plus 2 to the 5 times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And that was relatively painless. No huge quotient rules, no product rule within chain rule, within product rule, within quotient rule. Nothing horrible and scary like that. We're able to take the log and break this down into a bunch of little pieces. Each one is relatively easy to handle. I'd like you to take a second and look at your notes. So my last step here is to solve for y prime. Take a look at your notes and see if there are any steps here that you would like to talk about a little bit more. Okay. Can't quite get it all to fit on one thing here. So what would we like to talk about? What would we like to ask about? What feels weird or challenging, or what doesn't make sense?
So in that last step, we just plug y back in.
Yep. Yeah. So the result here was an expression involving y prime and y and all this stuff. So because I don't want any y's in my answer, I just want y prime equals whatever it is, only involving the variable x. I take this y and I plug back in, yeah, what I was originally told y is. So that's the last step there.
When we first differentiate, and like the 3/4 and the 1/2 and the -5 out in front, why don't those go to 0 when we differentiate that whole thing there?
If you have a constant hanging out on its own, that will differentiate to 0. But a constant multiplying a function pops out of the derivative. So remember, one of our older rules, yeah, definitely it's true that d dx of a constant is 0, but d dx of a constant times some function is c times f primed of x.
Oh, okay, so it's like
Constant
product
multiples pop out. Because there were multiples, they came along for the ride.
Okay, cool.
Yeah, fair question. I remember wondering that when I was a student. One fun way to play with this, you can expand this using the product rule. You can treat this as the derivative of that constant times f of x plus that constant times the derivative of f of x. The derivative of the constant is 0. So you can actually think of that as a consequence of the product rule. 0 times f of x is 0. I remember having to justify this to myself because it drove me nuts at first. But it does work, right? Totally kosher. But usually people just remember that constant multiples pop out. What else are we wondering? Right, I know it's a fairly involved problem. It's the first time we've done something like this, so I'd expect there to be some furrowed brows. Were we in person? I can't see your brows, but I trust that some of them are furrowing. What else are we thinking? Do we feel okay with this expansion step? The algebra here tends to be something that trips people up. Any questions about the algebra that we did before we differentiated? Cool. Okay then. Then I will go ahead and outline for you the basic procedure for logarithmic differentiation.
Mr. Koo, could I ask a quick little favor?
I'm sorry, I heard something there, but it was very quiet. Could you repeat that?
Could I ask a small little favor, please?
Maybe my speakers are quiet. Sorry, I'm doing my best to hear you. Could I ask you to just shout that or something? Maybe get a little closer to the speaker or the microphone?
Can you hear me better now?
Oh yeah, much better.
So could I quickly look at the previous page before this one? I wasn't able to write everything fast enough.
Sure. Let's see, are we on the reverse side of this? Yeah, this guy, right?
Yes, that one.
Okay. So that was actually us recapping the problem we had worked before, which started with, where did that go? Here, I got it down here.
I snapped the picture so you can move on.
Okay. So the order there was this, right? Are you comfy with that? If there's anything you want to fill in on your notes, it's all right. We can take some time here.
Thank you so much.
Yeah, of course.
That second to last line, is that 2 times x plus 12 or plus 2?
On the second to last line, so we're talking like here.
Correct.
This is 1 over x plus 1, and then I multiplied by 2 times x plus 2 over 2 times x plus 2.
Perfect. Thanks. Sorry, I was driving earlier.
Okay.
Thank you.
Yeah, I can zoom in a little bit. Okay. And then do we want to look for just a minute at the other one again? Make sure we've got everything in our notes good. We have this. All right, so we started here. I'll leave this up for just a second. Want to differentiate x to the 3/4 square root x squared plus 1 all over 3x plus 2 to the 5. So we start by taking the natural log of both sides. I had y equals that. Now I have ln y equals ln that. And then we expand everything out using our properties for logarithms. I'm just doing this so we can fill in any gaps in our notes. Once we have everything expanded as far as it can go, I differentiate on both sides implicitly with respect to x. So the derivative of ln y is 1 over y times y prime. And then over here, I break this down one piece at a time. The 3/4 comes along for the ride, and the derivative of ln x is 1 over x. The 1/2 comes along for the ride. The derivative of ln x squared plus 1 is 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, minus 5 times the derivative of ln 3x plus 2. And the derivative of ln 3x plus 2 is 1 over 3x plus 2 times the derivative of 3x plus 2, which is 3. I'm going to push the page up just a little bit. Because then our last step here is to solve for y. Solve for y prime, which means multiplying both sides by y. That gets rid of my 1 over y here. So I had 1 over y times y prime. I multiply both sides by y to get rid of the 1 over y. That gets y prime on its own. But y prime equals y times this thing. And then my very last step is to substitute in for y. Okay, so I am going to go ahead and move on. If you need to go back and rewatch this video and fill in your notes, I strongly encourage you to do so. Or you can come by office hours. I know my office hour last Friday ended up getting canceled. I'm really sorry about that. My wife needed me to go up to her work and help her out with some stuff, and it got way carried away. But I will have my normal office hour today. So,
I knew it. Congratulations, you got married.
yeah, so the coronavirus decided it didn't want us to get married in March. And then it started looking like our second wedding plans were going to get fucked up by coronavirus also. So we said, to hell with it, we're just going to go get it done.
Oh,
Ended
good.
up being a nothing special wedding, but we're going to do a nice celebration once it's over.
Good. Congratulations.
I appreciate that. That's really sweet. So the strategy for logarithmic differentiation goes as follows. First, take ln of both sides. Then expand the log stuff as much as possible. And then differentiate implicitly on both sides. And this is one place where people mess up. They forget to differentiate on the left. Differentiate both sides implicitly with respect to the variable x, or whatever your independent variable is. And then finally, solve for y prime. So this is the kind of algorithm, and it allows us to differentiate nasty big chunks like that without using the quotient rule, without having to touch the product or quotient rule at all. That's really nice. And at first it might seem like that's the only thing logarithmic differentiation is good for, but in fact there's more. But wait, there's more, Billy Mays. Billy Mays here for logarithmic differentiation. There's some stuff that we can't differentiate straight up. There are some things that don't fall under the quotient or product rules or chain rule even, at least not right away. And the famous example of this is the super exponential function x to the x. This is a weird function. You may have never seen it before. It's not an exponential because the base isn't constant. It's not a polynomial or a power function because the power isn't constant. It's definitely not a trig function or a log function. It's its own weird ass thing. The graph It's like this. Ignore the stuff on the left there. Here's the graph of x to the x. Very strange, right? Very, very strange. It grows fast. It grows way faster than like e to the x. Although it might not be obvious right away, you'll see over here they do cross and the red ends up above the blue. So it's a very, very fast growing function, but at the start it does some interesting shit. In particular, right here you see it looks like it has a horizontal tangent. Let's see if we can find this point where that horizontal tangent line occurs. That means I would need to find y prime and then find out where y prime is equal to 0. But when we look at this, I don't see any obvious way to find y prime. I definitely can't attack this with the power rule because the power isn't constant. And I can't treat this like an exponential function because the base isn't constant. But what I can do is differentiate logarithmically. So if I take ln of both sides, I'll number these steps here so you can see how they line up with the strategy described above. And then I'll expand everything as much as possible. On the right-hand side here, this power can come down. And that's really all the expansion that can be done. But that does the hard stuff, right? Now this is something I can differentiate. It's going to require a product rule, but it's not a bad product rule. It's fairly straightforward. So I'll differentiate on both sides implicitly with respect to x. And on the right-hand side there, that requires a product rule, but it's not a bad product rule. The left-hand side will be 1 over y times y prime. And my right-hand side, first I'll differentiate the x and leave the ln x alone. That's 1 times ln x. Plus, now I'll leave the x alone and differentiate ln x. That's 1 over x. I can simplify this a little bit. So I get 1 over y times y prime equals ln x, because 1 times ln x is just ln x. And then x times 1 over x, that's just plus 1. Which means y prime is y times ln x plus 1. So this would be my fourth step. And then I'll go ahead and plug in for y. So I get y primed equals x to the x, because that's what y is, times the ln of x plus 1, like that. So this is a derivative that we could not have found without using logarithmic differentiation. None of our other differentiation rules apply to that guy because that guy doesn't fall into any of the families of functions that those rules apply to, right? It's not a power function, not an exponential function, definitely not trig or anything like that. But if we take the log of both sides, it simplifies into something that we can differentiate. That derivative is not hard to calculate, but you do end up needing to multiply back over this y. And so I could find my horizontal tangent line by setting this to 0. So the way we took the derivative here, there's a question in chat. On the left-hand side, the derivative of ln y, derivative of ln of anything is always 1 over that thing times that thing primed. And on the right-hand side here, I'm using a product rule. So I've got 1 here, that's the derivative of x times ln x. So I differentiate the x, I leave the ln x alone, that's like f prime times g, plus f times g prime. The derivative of ln x is 1 over x. So I'm writing this as, I'll write out the schematic here. It's x prime times ln x plus x times ln x, all primed. And then x primed is 1. The ln x there comes along for the ride, plus x here coming along for the ride, times ln x all primed is 1 over x. Here to here, I cancel the x's. X times 1 over x, that's 1. And 1 times ln x, that's just ln x. Here to here, I multiplied both sides by y. And here to here, I plugged in for y. So that's the gist of logarithmic differentiation. And then if we wanted to do that thing, want to find that horizontal tangent line, well, that must occur when y prime is equal to 0. But I just found y prime, so that's the same as saying x to the x times ln of x plus 1 is equal to 0. Now, x to the x is either 0 or ln x plus 1 is equal to 0. Those are the two possibilities. All right, if you have two things multiplied together equals 0, then one of them has to be 0. Here, if you take the natural log on both sides to try and solve this equation, this is undefined. ln of 0 doesn't exist. So no solutions come from this guy. Here, if I want to solve this, I would subtract 1 from both sides. And then exponentiate on both sides to undo the log. E to the ln of x is just x. So this is x equals e to the negative 1, or 1 over e. And if you come back to our graph, here in just a second. Where is that? There we go, that's everything. All right, so we found our derivative y prime. And then if I wanted to find horizontal tangents, I need to set y prime equal to 0. Y prime is x to the x times the ln of x plus 1. This first piece yields no solutions. This second piece yields one solution. And if you come back to our graph, and you graph the line, there it is. Let's see, so sorry, I'm saying this wrong. If you look at the point on the graph there, so call this f of x equals x to the x. Then I look at the point, 1 over e, comma, f of 1 over e. You see, that's my guy right there. I have a horizontal tangent right here. All right, nifty. So how did we find this minimum, right? This is a local min where you have this horizontal tangent. How did we find that local min? We took the derivative and we set it equal to 0. And this is going to be a theme as we move into chapter 4. Okay. So this is the end of section 3.6, really. 3.6, short section, just talks about how to take derivatives by first taking the log on both sides. The main thing we're going to talk about this week is related rates, which is tied directly to these concepts of implicit differentiation and logarithmic differentiation. But the big game there is that we're now going to start talking about things in the real physical world. Or we're going to try to solve some problems that have to do with like movement by using calculus. And it's a big step. It requires you being absolutely comfortable with implicit differentiation. So I want to solve just one simple little problem like that for you guys.
Can you go back to the notes real quick?
Cool. Yeah. There you go.
Thanks.
So the homework that I'm going to pop open for you guys today will have a handful of logarithmic differentiation problems. But mostly I want you guys to be making sure that you have finished up the homework from last week on implicit differentiation. That way we can talk about related rates. We'll be able to talk about related rates in a way that makes sense. The famous introductory problem is a sliding ladder. So if any of you have ever been on top of a ladder painting a wall or trying to clear out gutters and you feel the bottom of the ladder start to slide away, it's a shit your pants moment. That happens to be a really good math problem. This will be our intro to section 3.9. Yeah. And this is a big section. Related rates. So remember, derivatives are rates of change. And so related rates are problems which involve one derivative or one rate of change affecting another. So imagine a ladder leaning against a wall. And we'll say the ladder is 10 feet. So here's my wall, here's the ground, here is my 10-foot ladder. And something terrifying starts happening if you're standing at the top of this. The ass end of this ladder starts scooching out that way. The base of the ladder starts to slide out at, let's say, 1 foot per second. I want to know how fast is the top of the ladder falling, right? If I'm at the top of that ladder, how hard am I going to bust ass when this thing finishes sliding? How fast is the top of the ladder, this point right here, going down? So can we all picture the physical situation? You've got something leaned up here, the bottom starts to slide out, so the top starts to slide down. And the connection between the two is fairly straightforward, but it's not naive. It's not, oh, well, the top is also falling at 1 meter per second or 1 foot per second. That much is not true. The way we're going to get this is by thinking of this distance here as x. And this distance here as y. Then by the Pythagorean theorem, because this is a right angle down here, x squared plus y squared is equal to 10 squared, or 100. Since the base of the ladder is moving out at 1 foot per second, remember this is my horizontal axis, it's my x-axis, this is my vertical axis, it's my y-axis. The derivative I'm interested in here is dy dt. how is y changing with respect to time? Since the base of the ladder is sliding out this way, x is getting bigger at a rate of 1 foot per second. So this tells me that dx dt, the change in x with respect to time, is 1 foot per second. So if I come in here and I differentiate this relationship, this is the equation that relates x and y. If I differentiate that relationship implicitly with respect to time, then I'll be able to relate the derivative dx dt to the derivative dy dt. So I apply the operator d dt to both sides. The derivative of the constant function 100 is 0. Over here, the derivative of x squared taken with respect to t is 2x times x prime, which I'll write as dx dt, to remind ourselves that it's a time derivative, times 2y dy dt. So this is differentiating implicitly with respect to the variable t. So I treat y the same way I normally would, right? I'd normally, if I'm implicitly differentiating y squared, I would get 2y times y prime. Instead of writing y prime here, I'm just writing it in the Leibniz notation to remind me that the derivative is not with respect to x, but with respect to t. What we discover is that the answer to the question, how fast is the ladder falling, depends on not just x and y, but also on their time derivatives. So here I'll plug in 1 for dx dt, and I get 2x times 1 plus 2y times dy dt equals 0. I can solve that for dy dt. And I get 2y dy dt equals negative 2x. I divide both sides by 2y, and that gives me dy dt equals negative x over y. So if I want to know how fast the ladder is falling, I have to ask, well, at what time or at what point? So where is the ladder right now? If the ladder is at the position, let's say y equals 8 and x equals 6. So when the base is 6 feet from the wall, the top is 8 feet off the ground. The ladder will be falling, the top will be sliding at the rate. I come here and I plug in dy dt is negative of the wall. So if the base is 6 feet, that means x is 6. So negative 6 over the top is 8, negative 6/8. And if you divide top and bottom by 2, you get negative 3/4 feet per second. So if in that moment, the bottom is moving out at 1 foot per second, the top is moving down at 3/4 feet per second. The negative tells you it's moving down, and then 3/4, that's how fast, moving down at 3/4 feet per second. In other words, the top is falling a little slower than the bottom is moving out, right? 3/4, a little bit less than 1. This is a classic related rates problem. It's going to take a little bit of time to get comfy. First, the idea of a third variable here, right? We've got x and y, but both of those are spatial variables, and we've also got time involved. Here I'm thinking x and y is changing over time. The implicit differentiation we should be pretty comfy with, but maybe we haven't been using Leibniz notation a lot. So we're going to want to get used to that, the dy dx, dy dt notation. And then finally, really the hard part is usually setting up the problem. Usually the hard part is finding a way to go from a picture like this to an equation like this, where you can differentiate, and then also figuring out what each thing means and what to plug in. So they're word problems, right? They're hard word problems. They're calculus word problems. Section 3.9, I fully expect to be challenging for pretty much everybody. It was challenging for me when I learned it. It's been challenging for pretty much everybody I've seen learn it. So we're gonna move slowly. At the start of class next time, I'm gonna begin by practicing some more implicit differentiation stuff. We're gonna practice differentiating shit like this with respect to some third variable t, just to get you used to the mechanics. And then we'll start working some more related rates problems. I'll show you a handful of other like classic physical situations that are easily modeled like this. And we'll move on from there. The next topic after related rates is some other kind of non-obvious application stuff like linear approximation. And then once we finish with those applications, min-max problems, linear approximation, and excuse me, then we'll be ready for the test. There's a theorem called the mean value theorem that we're going to talk about. But this is where we're going. So we're going to solve some related rate stuff. Then we'll solve some optimization stuff, finding mins, finding maxes, kind of like we found this min right here by setting the derivative equal to 0. And then we'll be ready for exam 2. So I'm thinking probably next week we'll go over the mean value theorem, the linear approximation stuff, and min-max stuff. And then probably the week after that, we will be ready for test 2. So I know it feels like these are coming fast. That's just kind of how the summer courses are. If you need more time on the most recent homework, please go ahead and submit an extension request now, and I will get in there and clear those out as soon as I can. And then watch for the new homework to open up today. Oh, good question. Yeah, so the college is officially closed on the Friday, I think. Yeah, the 3rd. Shit. That's gonna set us back a little bit more. Okay, that might affect the scheduling for the exam. No, we will not have class on Friday. Friday is an acknowledged holiday by the college, even though it's not the 4th of July, just because the 4th happens to fall on a weekend. So we'll have class on Wednesday. I will show you guys the related rate stuff then, and we'll kind of play it by ear, I guess, moving forwards from there. But we're somewhere around 2 weeks out from test 2. I just wanted to give you that heads up. Okay, so be working on the WebAssign stuff. I'll come in here and clear out any extension requests that are there right now. And if you need more time, I guess I'll wait a few minutes to get to do that. So go ahead and submit an extension request if you need it for homework 6. At the start of class next time, we'll do some more implicit differentiation to practice finding things like this. And then we'll move forwards with related rates problems, okay?
Mr. P, I have a really quick thing to say.
Yeah, what's up?
So I tried to do an extension request on the previous homework, but I couldn't do it. That's why I emailed you. So I don't know if just like something that I don't know how to do.
Oh, that's fascinating. So here, I'll open the student view and take a look. No, go away. An option, calc 1. All right, so if I needed more time on a homework, when I click on I go to my assignments, past assignments. Down here, there should be a request extension option. If you don't see,
It didn't let me go through. It wouldn't let me pass it through after I opened it.
Ooh, that's strange. Do me a favor, take a screenshot, whatever it shows you when you do that, send it to me, and we'll talk to the Cengage people, see what's going on. You can open a support ticket with them yourself, but also send it to me, because usually they respond a little bit quicker if the professor leans on them. So you're saying you get to this page, but when you click on this, it won't let you like fill it out?
It won't let me just do anything. I tried writing something and then choosing numbers, and then the submit button will not allow, it will not change to blue.
Did you click on the calculator like he's doing right there? Or not the calculator?
Interesting.
Calendar?
Yeah, I'm not sure why that's the case. Aubrey, did you hear what Angelica said? I couldn't quite hear what she said either. Angelica, could you repeat that a little louder?
The calendar. Sometimes I don't click on the calendar and it won't let me do it.
Oh, I see. Yeah, so when we come in here and it won't let you like select a day, is that the idea?
Yeah, it won't let me submit unless I click on the calendar. So if I type in the month, day, and year, it won't work.
Oh, I've encountered that also. Yeah, so WebAssign is very finicky about their formats for dates and times. So it might be easier, Aubrey, give it a try. Go in there, select the calendar, and then use their little time thing here and see if that works. But if that doesn't work, then we need to open a support ticket with Cengage.
Okay, thank you so much.
Of course, yeah.
Office hours today, correct?
Yep, I'll have my regular office hour from 1 to 2 p.m.
Cool. See you then.
All righty. Take care, guys, and I will see you on Wednesday.